Welcome to this explainer. We're diving right into the core architectural showdown that is literally defining local AI in 2026. If you've been following the massive shift away from cloud reliance and toward running artificial intelligence entirely on your own hardware, well, you know that the silicon you choose dictates absolutely everything about what you can actually build. Today, we're breaking down this fascinating battle between traditional PC discrete GPUs and Apple Silicon's united memory architecture. Okay, it really all boils down to this central question. What exactly is the ultimate hardware for localized intelligence? Are you after blistering, uncompromised speed, or do you desperately need the sheer capacity to run massive frontier-class models? As we'll see, the engineering philosophies behind standard PCs and Apple Macs have violently diverged, and your choice is going to drastically impact your setup. Now, to wrap our heads around this battle, we first have to meet our main antagonist. It's known as the memory wall. You know, getting an AI to generate tokens, basically spitting out words piece by piece, isn't actually constrained by how fast a chip can do math. Not at all. It's a physics problem. It's all about shuffling massive amounts of AI data around. The memory wall is that physical limitation of moving billions of model weights from your storage into memory and finally into the processor fast enough to give you a real-time response. Honestly, it's a total data logistics nightmare. Think of moving all this AI data just like physical logistics. If you need to move mountains of goods, are you going to choose a blazing fast sports car on a short track or a massive heavy-duty freight train? Keep that exact analogy in your head, because it perfectly explains why a top-tier Windows PC and a top-tier Mac behave totally differently when you ask them to run a large language model. Section 1. The PC GPU and the absolute pursuit of raw speed. Whether we're talking about NVIDIA's RTX 40 series or the brand new 50 series, traditional PC GPUs are the undeniable kings of raw throughput. Take this staggering number, 1,792. That is the gigabytes per second of extreme memory bandwidth you're getting on something like NVIDIA's RTX 5090. Because generating tokens is such a memory-bound process, this massive data pipe lets high-end PC GPUs spit out like 150 to over 200 tokens per second for an 8 billion parameter model. To put that in perspective, that's roughly 5 times faster than you or I can even read. But, and there's a big but here, that blistering speed is tightly constrained by a very fixed physical limit. PC GPUs have dedicated video RAM or VRAM. An RTX 4090 has 24 gigabytes, a 5090 has 32 gigabytes. Now, if your AI model is just too big to fit inside that dedicated VRAM, your system has to offload layers to your regular system RAM. And when that happens, yeah, your performance drops off a total cliff. Basically, a model that fits in VRAM is going to run about 10 times faster than one that spills over. So the crucial takeaway here is that a PC GPU is absolutely your sports car. It gives you incredibly fast inference, but you have a very tiny trunk for your AI models. Even if you use advanced 4-bit quantization to shrink those models down, you're generally stuck running a maximum of 32 billion parameter models on a single high-end consumer GPU. If you want to run a massive 70 billion parameter model, well, get ready to buy multiple very expensive GPUs just to split up the workload. Section 2, Apple Silicon and the massive shift to unified memory. When Apple moved to their M series chips, they entirely ditched the whole concept of having separate system RAM and GPU VRAM. Instead, they built a unified memory architecture that scales up to an unbelievable 512 gigabytes. That is a massive pool of memory accessible on upcoming setups like the Mac Studio M4 Ultra. Since the CPU and the GPU share the exact same memory pool, the GPU can just access the whole thing. So basically, if you have a Mac with 128 gigs of RAM, you effectively have a 128 gigabyte GPU. It's wild. And this completely rewrites the rulebook by loading the entire model directly into that unified memory, meaning absolutely zero GPU to CPU transfers. Apple completely wipes out those data transfer bottlenecks that cripple discrete GPUs when models get too large. You literally just avoid that VRAM capacity wall entirely. Going back to our logistics analogy, Apple Silicon is definitely the massive freight train. Its memory bandwidth is lower, around 800 gigabytes per second, compared to NVIDIA's 1,700 plus. So yeah, it moves slower. You might only get 12 to 20 tokens per second, but it can carry enormous 70 billion, 100 billion, or even 200 billion parameter reasoning models in a single trip, all on one desktop machine. That's a capacity feat a single PC GPU just simply cannot pull off. So here's the side-by-side showdown, extreme bandwidth versus endless capacity.
If you need 100 tokens per second for real-time, snappy, interactive chat, the PC GPU wins hands down, no question. But if you want to run massive things like DeepSeek R1 or Llama 3 70B locally for deep, complex reasoning, and you're perfectly fine with 12 tokens a second, Apple's unified memory is absolutely the most elegant solution out there.
Section 3. Let's talk about power and efficiency trade-offs. Because raw performance definitely isn't the only battleground here. The second you start running local AI 24/7, the energy divide becomes pretty staggering. Just consider this. High-end PC GPUs are absolute power-hungry beasts, demanding 450 watts or more under full load. Meanwhile, Apple's ARM-based architecture basically sips power. An M4 Max uses roughly 60 watts under full GPU load. We're talking about a fraction of the power for some highly capable inference. If you care at all about your monthly electric bill or just keeping your office when turning into a total sauna, these efficiency trade-offs are crucial. When you're designing an always-on AI assistant, a PC GPU setup means massive 850 to 1200 watt power supplies, heavy-duty cooling, and it can literally add $50 to $150 a month just in electricity. On the flip side, specialized neural processing units, or NPUs, alongside Apple Silicon, give you 3 to 5 times better performance per watt. That makes them perfect for quiet, cool, always running workflows. But hey, here is the absolute best thing about local AI. Zero. Despite the upfront hardware costs and whatever power you're drawing, running local inference on either of these architectures drives your marginal cost per token down to exactly $0. Whether you go with the sports car or the freight train, once you actually own the hardware, you are completely free from Cloud API subscriptions and those annoying per-token fees. Section 4. Choosing your AI setup. So how do you actually translate all these fascinating architectural differences into a real purchasing decision? Well, it's all about matching the hardware right to your specific workload. If you're a developer and you need blazing fast code generation from an 8 to 32 billion parameter model, you grab the PC Discrete GPU for that extreme bandwidth. If you're tackling deep reasoning on sprawling 70 billion plus models and you really don't want a noisy server rock in your room, Apple Silicon's shared memory pool is your clear winner. For mobile, always on battery life, you want to lean on NPUs. And if you need to serve multiple users concurrently, well, you scale up by linking multiple PC GPUs together.
To wrap up this explainer, I want to leave you with this provocative thought. As models just keep growing and optimization tricks like quantization get even better, which engineering philosophy is ultimately going to win the battle for your desk? Are we going to figure out a way to give PC GPUs enough VRAM, or will unified memory speeds finally catch up? This localized intelligence revolution is honestly just getting started, and the hardware choice you make today is going to dictate your capabilities tomorrow. Thanks for tuning in, and keep experimenting.